Hello and welcome. If this is your first time here, welcome to the channel. And if you've been following along with the PIW-CWG series, thank you for coming back and spending this time with me. Today, I want to talk about something that sounds counterintuitive at first, but sits very comfortably inside modern cosmology once you slow down and think it through. This isn't a metaphor, and it isn't philosophy. It's a physical idea about how information behaves in the universe. This episode is called Void Record Theory, and the basic question is simple. How can information persist in regions where matter disappears? Most of us instinctively associate memory with substance. We think records need material: books, disks, fossils, structures. More matter feels like more memory. Less matter feels like loss. But the universe doesn't actually preserve information by holding on to it tightly. It preserves information by not erasing it. And erasure happens through interaction. Wherever matter is dense, interactions are frequent. Particles collide, energy gets exchanged, systems mix, heat flows, structures form and dissolve. These environments are active and productive, but they're also noisy. Fine-grained details don't last very long unless they're constantly reinforced. Matter is creative, but it's also forgetful. Stars, galaxies, planets, and plasma fields are places where information is constantly being overwritten. Now contrast that with the largest, quietest structures in the universe: cosmic voids. Voids aren't completely empty, but they are regions where matter density is extremely low. Fewer particles, fewer collisions, less mixing, less heat, less disturbance. And that changes everything about how long information can survive. When interactions are rare, erasure slows down. Void record theory starts from that observation. Information doesn't vanish just because matter leaves a region. In many cases, once matter evacuates an area, the remaining structure, the geometry, the expansion history, the large-scale configuration, can persist with remarkably little modification for extremely long periods of time. Voids don't actively store information, they simply fail to destroy it. This is where our intuition usually breaks. We tend to think of emptiness as absence, as nothing worth paying attention to. But in cosmology, emptiness can function like an archive, not because it remembers deliberately, but because there's nothing around to overwrite what's already there. As the universe expands, matter flows along gradients. It drains out of some regions and accumulates in others. Dense regions get denser and voids get emptier. That flow doesn't erase the past. It redistributes it. And once a region becomes sufficiently empty, its large-scale features change very slowly. Expansion stretches distances. Dilution lowers interaction rates. And without frequent interactions, the universe stops scrambling information in those regions. In that sense, voids are low-noise environments, and low noise is exactly what long-term preservation requires. This doesn't mean voids contain hidden messages or detailed snapshots of the past. It means that certain kinds of information, statistical structure, large-scale correlations, expansion history, survive longer in emptiness than they do in crowded environments. Dense regions are busy rewriting themselves. Voids are quiet enough to keep old constraints intact. This idea already shows up indirectly in how cosmology works. When we look at the largest scale structure of the universe, voids help define the cosmic web. They preserve the imprint of early expansion, matter flow, and gravitational shaping because nothing has come along to significantly disturb them since. In other words, some of the universe's longest-lived records exist where almost nothing is happening. That's not a poetic statement, it's a physical one. Information doesn't require observers. It doesn't require intention. It doesn't require storage devices. It only requires that the universe doesn't allow a process to be undone. Wherever erasure is slow, history lingers. Void record theory is not saying that emptiness is special or mystical. It's saying that interaction destroys detail, and the absence of interaction preserves it. That's a rule that applies everywhere. Voids are just where it becomes easiest to see. This also reframes how we think about loss. When matter leaves a region, we often think something has been erased, but in many cases, what's really happened is that erasure has stopped. The record isn't gone. It's just no longer being rewritten. That idea will matter later in this series when we talk about horizons, entropy, collapse, and renewal. For now, the key takeaway is this: the universe remembers unevenly. It remembers best where it is quietest. If you've been listening carefully, you might notice how this fits with the larger PIW-CWG picture. Persistence doesn't mean stasis. It means duration under constraint. Voids are not frozen. They are simply constrained in a way that protects certain information from being erased. Before I close, let me say thank you for taking the time to listen to this video. These episodes are meant to be slow and deliberate because the ideas only make sense when you give them room to settle. My name is Charles Carroll, and this is part of the PIW-CWG series. In the next episode, we'll look at how structure rearranges without resetting, why the universe shuffles its patterns instead of starting over. Thanks for being here.